In this series of videos, we're going to explore the topic of tension, which at times can be challenging for physics students to understand because it's not an obvious force like a contact force or gravitational force. So what we're first going to do is just simply define what tension is. It's a force that exists in a rope or a string that is holding or pulling something. So in this case, our very simple case of this weight, this 10 kilogram weight hanging from a ceiling, we just have the tension T that is going to be pulling upward in that direction. So if we kind of just, think about there's tension pulling upward here, and then the other thing that we have is gravitational force pulling it down. So if we kind of did this as a force diagram, here's our tension, and here's our weight. And I apologize for the crooked arrow, but I think you got the idea. We need to remember that this is something that is in equilibrium, which basically means that the sum of the forces that are acting on this are equal to 0. So as I fix this, I have the tension moving up, and I'll go back to this idea. The sum of the forces acting on this are equal to 0. So the forces that I have are the tension and the weight. So weight is equal to mass times gravity, which in this case would be 10 kilograms times 9.8 meters per second squared. When I multiply those two things together, I get 98 kilogram meters per second squared, or newtons. So I need to define a positive and negative direction now that we've figured out what our weight is, and we're going to say the things that go up are positive, a very common notation in physics. So my forces in this case are going to be the tension, positive tension because it goes up, minus the weight is equal to 0. Tension T minus the weight of 98 newtons is equal to 0. Solve this for T. T is equal to a positive 98 newtons. So what we find out in very simple cases like weights hanging on strings, the tension is just simply equal to the weight of the object on the string. What we want to do is look at a little bit more complex cases. And here we have 3 different tensions that we're asked to solve for. T1, T2, and T3. And we're going to kind of start with T3 because it's very similar to what we had before. If you took these 2 cables off the top and you just had a single 1 cable hanging here, you probably pretty much see that it's the same as what we just did. The sign has a weight of 200 newtons, so we could just simply say, okay, well, T3 is going to equal 200 newtons based on the same idea we just used. So we found one of these without doing any math at all. The thing that this problem is a little more complicated than the previous one is we have 2 different dimensions that we have to account for. We have the x dimension, which moves to the right and to the left. That would be T2, and this component of T1, which we're going to call T1x, and the y dimension, which moves upward or downward, and that would be this component of, we're going to call it T1y, and this other vector, T3, which we just found. So, same idea. We're going to start with the sum of the forces has to equal 0, but we have to go a little bit more. The sum of the forces in the x direction would equal 0, and the sum of the forces in the y direction have to equal 0. So we can't just start with, we can't do all of these at once. We have to kind of make sure everything pulling it left and right and cancel out, and everything making this go up and down cancels out. We're going to start with our sum of the y forces. I'm going to change color here just to kind of show that this is where we're going. And so the sum of the forces in the y direction equals 0. Now, when we look at it, the only forces that go in the y direction are this T1y right here that I'm trying to shade over, and this T3 going down. Everything else is moving the opposite way. So just like before, I need to say, okay, I want to define up is positive, and we'll say going to the right is positive. So because up is positive, my T1y is positive, but minus T3, and that equals 0. Now filling in my numbers, T1y, we don't know yet. T3 we know is 200 newtons, that equals 0, so then T1y is equal to 100 newtons. So it kind of shows us that as long as you know one of these cable forces, we can use our ideas of equilibrium to eventually get to the idea of what one of these forces are. Now that we understand this, we are left with a right triangle that we can use our trig functions to solve for. So we have 200 newtons here, we have 40 degrees here, and we have an x and a hypotenuse, so T1, over here. So to find this x function, I would then use the tangent function. So I'm going to say, all right, well, tangent of 40 degrees is equal to T1x, we'll call it, over, oops, I have that backwards, sorry about that. It's going to be the opposite side, not the adjacent side first. So it's going to be the 200 newtons over T1x. Now this one's a little bit more complicated because you got to multiply, cross multiply here. You're going to get T1x times the tangent of 40 degrees is equal to 200 newtons. And then you solve for that, and T1x is going to equal 238 newtons. Now that should make sense, that this is more than the value of the weight of the sign. And that's because we have these different cables kind of working against each other, pulling against each other, and some of their force is not used to lift this sign up. It's to kind of counterbalance it. So this is an okay value right here. And now what we need to do is find the tension. In this case, this would be tension T1. And we can just use the Pythagorean theorem for that. So it's like T1 squared is equal to T1x squared plus T1y squared. And T1x we just found is 238 newtons squared plus T1y, which is 200 newtons squared. And when I add these together, I get 96,644. Obviously use my calculator to do that, newtons squared. Take the square root of each side, and I get T1 is equal to 310 newtons. So working through, I found T1, 310 newtons. I found T3, the weight of the sign, 200 newtons. I'm still looking for T2. However, I'm going to use this little space on the side here because I'm getting a little bit short. I got to remember that the sum of the forces in the x direction equals 0. Well, when I'm talking x forces, I just have this and T2. So I end up with T2, negative T2, because we said that's negative when you go to the left, plus T1x, which should be 238, is equal to 0. So then I end up with 238 newtons is equal to T2. So that's how you find the three tensions holding up our E at Joe sign here, using the idea of equilibrium and tension.